Hey y'all, in this lesson, we're going to look at continuous compounding interest. This one starts with a little bit of a story, but basically there were three people in the 17th century around that time that were kind of working on the same problem. We do call it Euler's. It's spelled E-U-L-E-R, but Euler's constant E. But basically they were looking for the same thing. So essentially, a banker was looking into a financial problem that if we had a compounding interest problem, if we were to compound more and more and more over and over and over again, like would that converge to a specific number? And it did. It converged to the Euler's constant called E. And that is about, it's kind of like pi. E represents a number, pi represents a number. It converges to about 2.72 if I were to round a lot. But this is going to help us with our continuous compounding interest problem. So when I say converge to this, it's like when you do smaller and smaller increments and get closer and closer and closer, it kind of converges to this point, and this was that point. So the formula for this is a simple one. It is A equals P times E to the RT. I call it APERT, so it's easy to remember for continuous compounding. So if you're doing a problem and you see continuously or continuous, then you know you're going to be using this formula, APERT, where E is essentially just a constant and we're raising it to rate times time. And P would be that principal amount. This is not necessarily like a common type interest that you can't really go to a bank and like ask for this, but there are, I think, some retirement things or there's special cases where this is used. So in these problems, we're looking for a future value of continuous compounding. So there's our clue there that we're using this formula. So it has to say continuous. It doesn't have an N like we did in the previous compounding problems because it's continuous. It's compounding over and over and over and over and over again. So we have 950 is deposited at 1.7. So I'm going to convert that to decimal for 4 years. And then you just type that in and see what it comes out to. Now in your calculator, you might be wondering where the heck is E? So I'm going to show you. If you can locate the LN, natural log, LN button, there's a little E there in the top corner. On mine, it's orange. So I need to grab the second button, second LN, and that grabs the E that I'm looking for. Yours might have like a little caret after, depending on your calculator. Mine automatically raises it to the exponent. So depending on what that looks like, in either case, you're going to put that rate times the years. And I don't need anything else, so I don't need to get out of that. You can close the parentheses if you have parentheses there, but it should look exactly like what you wrote down, and then hit enter. And we get $1,016.85 since we're rounding to the nearest cent, because in money problems, that's what makes the most sense. Anyway, that's what you should get for that problem. This next one's kind of interesting because it has the time given in months. And remember that for time, we want it in years. And I would avoid rounding as much as possible, because if you round in an exponential problem, your rounding is going to be exponentially off. So don't do that. Let's plug in our information. We have P E to the R, convert to decimal, times T. I'm going to write that as 34 over 12, and I'm going to leave it like that. Do not want to round. So I did 34 over 12 because it's in months. So I divided by 12 months to get it into years. And then to type that in, we have 2750. Whoops, 2750. There we go. Second ln 0.029. And then I'm going to do parentheses 34 over 12. So depending on your calculator, some of the older calculators have the little caret and it'll automatically have a parentheses for you there. So at the very end, you're going to have like a double parentheses. So anyway, it should look, you'll have more parentheses than I do, but it's okay. As long as when you hit enter, you get this amount, then you typed it in the right way. So we get 2,985 and 50 cents. So that's it. That's all you have to do for continuous compounding. The last thing we're going to cover in this lesson is years to double. This is also referred to as the rule of 70. So when working with inflation, which we talked about in the last video, we use a rule of thumb for computing quick estimates. And this rule of thumb is called years to double. We have this formula and we do 70 divided by the annual inflation rate. So in this example, we have estimate the years to double for an annual inflation rate of 2.4%. So we're just going to plug that into our formula. And we're going to go ahead and leave the percent as a percent here. If you change it to a decimal, then you'll have to change it back at the end. So we're just going to save a step and we're going to say years to double equals 70 over our percent. And then when you type that in to your calculator, pull that up, 70 divided by our percent is about 29 years. And that's all it needs. So if you were given the years and you were looking for this amount, you would have to do a little bit of manipulating to solve. I don't think you're going to have to do that, but that's all I have for years to double. So that's all for this lesson. If you have any questions, please let me know. I'd be happy to help.